Okay, so welcome everyone. So today we have Will Sawin from Columbia University speaking about the Shafarevich conjecture for hypersurfaces in abelian varieties.
Thank you. And so everything I'm going to say is joint work with Brian Lawrence. So let me begin with a classical topic in number theory, which is Faultings Theorem, formerly Shafarevich's conjecture. And so this is going to be about an abelian variety over the rational numbers. And we say the abelian variety has good reduction at a prime p if we can extend it from the p-adic numbers to the p-adic integers in some way that's smooth and proper scheme. So if the equations define a smooth variety mod p, and so we know that any abelian variety will have good reduction away from finitely many primes. And so Shafarevich conjectured what would happen if we fix a finite set of primes S, and we ask for all abelian varieties with good reduction at every prime not in S, or at least all abelian varieties of a fixed dimension n. So this was proven by Faulting. He proved that there are only finitely many such varieties of dimension n over the rational numbers with good reduction of all primes not in S, considered naturally up to isomorphism. And so this is about the strongest result you could hope for. I guess the only stronger result would be an exact formula for the number of isomorphism classes, and I don't think anyone suspects that such a formula should exist. It's a very powerful result. It implies Faulting's theorem about finiteness of rational points on curves, and implies some other useful stuff. So this result, and almost every result I'm going to talk about today, is also true. It also proven the same way over number fields. We're just going to restrict to the rational numbers just to keep the notation a little bit simple. So after Faultings proved this, people started thinking about like other classes of varieties where we could hope to prove a similar statement about there's finitely many with good reduction outside a fixed finite set of primes. And this is now known in a pretty sizable number of different cases. The main ones being K3 surfaces, del Pezzo surfaces, flag varieties, certain complete intersections, surfaces fibered smoothly over a curve, and Fano threefolds. And so for a lot of these, the method of proof uses Faultings theorem in a fundamental way. The key strategy is from one of these varieties, like from a K3 surface or from certain complete intersections, you can construct an abelian variety by geometric means. And then
what are the complete intersection situations?
So what you want is the complete intersection situation. You want those complete intersections where the middle row of the Hodge diamond has only two non-vanishing entries. Because in those situations there's an intermediate Jacobian construction that constructs an abelian variety from.
Right, so it's sort of a fake. I mean, if I ask you about hypersurfaces and projective space, you're telling me only for K3 surfaces.
Yeah, well, on this slide, yes. On a later slide, I'll have further information about hypersurfaces and projective space.
Okay.
But it's not just K3 surfaces. No, it's cubic threefolds are the very interesting case where they have the intermediate Jacobian.
No, are you
have a question? Oh, you're muted, I think.
sorry? Can I say? Yeah.
Yeah.
Are you talking about finiteness of the Shafarevich only in a higher dimension? Or are you talking about finiteness of rational points on certain varieties?
Isomorphism classes.
Okay, so it's not, because of course he has a second theorem which is much more powerful, which gives finiteness of rational points in many cases from subvarieties of abelian varieties. Right.
Yeah, that's a different theorem.
Right, I know. But
it has much less of a relationship with the main theorem of this talk. So I don't talk about it. That's also a great theorem. In some versions of this talk, I've explained that
theorem.
it is not so related to what I want to talk about. Yeah. So for this result of John Pager and Lugren, yeah, it doesn't handle very many hypersurfaces. I think the cubic threefolds are the kind of the main case of interest where that works. And there are some other complete intersections where you can do a similar argument. And then, I mean, a lot of these you could, it's often kind of a trick. Like the trick is like you show from one of these varieties, you like produce an abelian variety, and then use finiteness of the abelian variety, and then you try to use that to produce finiteness of your original variety. So what I want to talk about is another theorem along the same lines, which doesn't rely for its proof on Faultings theorem at all, but which abelian varieties are still very heavily evolved. So what I want to do is remember one of the abelian varieties from the last slide. So they're still defined over Q, and they still have good reduction away from S, still have dimension N. And let's look at hypersurfaces inside those abelian varieties, codimension 1 subsets. And we say, well, let's look at when those hypersurfaces have good reduction. And we'll say a hypersurface has good reduction if its closure in the unique p-adic integral model of the abelian variety remains smooth. So I don't care if it maybe has a smooth proper model embedded in some other variety. And then for abelian varieties, the dimension was the only topological invariant. For hypersurfaces, there's another topological invariant, which is their class. You can think of this in an algebraic geometry way as the class in the neuron severity group. You could also think of it as the homology class represented by the hypersurface. We'll fix that class, and to make things as non-trivial as possible, make the class ample. So the theorem we proved is that there are only finitely many smooth hypersurfaces in our fixed abelian variety, representing a fixed ample class phi with good reductions at all primes not in our fixed finite set S up to translation, as long as the dimension is greater than equal to 4. So we need to say after translation, because you can translate your hypersurface by a rational point in your abelian variety, and it'll still have good reduction in the same set of primes. And then we have this assumption n greater than equal to 4, which is more technical, but I can show you what happens in the lower dimensional case as well.
So how is this kind of good reduction is somehow more, how is it related to good reduction, meaning a proper smooth model at P?
So it's perhaps stronger. It may be stronger than good reduction in this proper smooth model. It's certainly not weaker, because yes, this always gives you a proper smooth model.
Yes.
And so I think it's quite possible that the method could be generalized to handle an arbitrary proper smooth model, but it's already a somewhat kind of random problem that it didn't seem like a very big deal. And also we don't have any examples, I don't think. Some people tried to find a proof that this is equivalent to good reduction in terms of a proper smooth model exists, and they neither proved it nor disproved it. So I don't know. But this is just the most convenient setup to work in. Yeah, so this is, like Faultings' other theorem, it involves subvarieties of an abelian variety, and it involves rational points, but that's sort of the only relationship. Does anyone have other questions about this statement?
So I guess another thing you could do is do automorphisms of A, but then I guess you get a different class if you take some sort of, right?
Yeah, so I think we checked at some point that there are finitely many ample classes of a given degree up to automorphisms of A. I mean, there's finitely many automorphisms that fix a given class, so you don't need to care about those. There's finitely many classes of a given degree up to automorphisms. So you could also phrase this of hypersurfaces of a given degree up to translation and automorphisms if you wanted. And you can, in fact, so maybe a more natural statement would be to combine our theorem with Faultings' finiteness theorem and prove a finiteness statement for pairs of an abelian variety and a hypersurface in that abelian variety. You have some options. You can do what you want. we're trying to like, isolate the most important or the hardest part. So feel free to interrupt with questions at any time. One question that you might have is what happens if n is less than 4? And so in the n equals 3 case, we can prove the same theorem, but it's a little more complicated to state. So we have this nice sequence of numbers, which goes 1, 5, 20, 76, and increases like exponentially after that. And from it, we form a sequence of binomial coefficients, which is you take two numbers from each adjacent pair of numbers in the sequence. 1 plus 5 choose 1, 5 plus 20 choose 5, 20 plus 76 choose 20, and so on. And the theorem in the dimension 3 case is the exact same statement. We have finally many smooth hypersurfaces representing phi with good reduction in all primes not in S up to translation, but with an additional assumption, which is that the degree of the hypersurface or the intersection number phi dot phi dot phi is not a multiple of any of the binomial coefficients on this list except possibly the first one. So the first one is 6, and this intersection number is actually always a multiple of 6. So it's very good that we don't assume that it's not always a multiple of 6. But the next number on the list is like in the tens of thousands, and they're growing super exponentially after that. So this condition of not being a multiple is a very mild condition. And almost every equation you can write down will probably have a degree that's not a multiple of one of these.
So is this an artifact of the proof, or is this or their actual counterexamples?
This is an artifact of the proof. In fact, it's sort of like triply so, because we prove it using one theorem, and we don't have counterexamples of that theorem, and then we prove it using another theorem, we don't have counterexamples of that theorem. When you prove it using like a third theorem, and like a couple layers down, you get to the case where we actually do have counterexamples, but it's very far removed from where we started off originally. I mean, this will be more clear what I'm talking about, at least a little bit, going through as I go through the talk.
I'm guessing that because phi is ample, the triple intersection number is never 0.
Yes, exactly. And so one other thing is for n equals 2, a hypersurface in an abelian surface is a curve. And you can prove the statement in n equals 2 case basically just using Faultings fineness theorem for curves. But that kind of method won't work in greater generality.
But there you're saying that the two kinds of good reduction are the same for curves and the abelian surface.
You only need the implication in one direction. You only need the good reduction in our sense implies good reduction in the abstract sense of the curve.
To infer your finiteness, okay.
Yeah. And then the curve's the implication is like strict, and the is strict, so it doesn't imply the other way. And in higher dimensions, maybe we don't know whether it's strict. It's not obvious. To understand our result, the most important prior work is not either a Faultings theorem, but the prior theorem of Lawrence and Venkatesh, which is about hypersurfaces in projective space, in case you wanted to know more about that. What they proved is that of hypersurfaces of degree d in projective space with good reduction of the primes not in S is not Zariski dense in the moduli space of all degree d hypersurfaces. So this is weaker than finiteness. They only prove that there's some polynomial equation which is satisfied by the coefficients of all hypersurfaces with good reduction, which is not satisfied by the coefficients of all hypersurfaces, and they prove this on some assumptions on n and d, which are completely explicit, but are complicated to write down, so I won't write them down. They roughly have the form that n should be sufficiently large and d should be sufficiently large as a function of n.
And again, is it known to be false if you don't make these assumptions, or is it artificial?
No, it is reasonable to conjecture a much stronger statement, which is for, I think, any n and d, that there's finally many hypersurfaces with good reduction up to linear automorphisms of the projective space. And it is, yes, and it's an artifact of the proof of the method that they're not able to prove that stronger statement that they need an assumption on N and D. And I'm going to sort of explain a little bit about why that's a restriction of the method, because it'd be helpful to understand what we're doing. So the shortest possible summary you could give of what Brian and I did is we took the same strategy, we introduced new ideas, and we were able to prove a stronger result. We were able to prove the full fineness and not just non-density, albeit in a different setting. We had to move from hypersurfaces in projective space to hypersurfaces in Abelian variety. And so what I will do in the rest of the talk is try to fill in more detail in that summary. So I'll begin by saying something about the method of Lorentz and Degenteich. So it's helpful to think here in a greater level of generality. Let's think about a general variety, and we want to show finiteness of the S integer points on that variety. So when X is the moduli space of smooth hypersurfaces in an Abelian variety or in projective space, this will be equivalent to finding hypersurfaces in the Abelian variety or in projective space with good erection. And you know, one can't prove fineness in general for many reasons. One is that many varieties do have infinitely many integer points. So we're going to assume we have some structure. And the structure I want to assume is we have a smooth proper map from some other variety y to x. And then in our moduli spaces, this will be the universal family over the moduli space. We'll have a family of hypersurfaces. And then a very powerful tool that we can use to attempt to prove fineness theorems is the Galois action on the cohomology of the fiber. So I guess in Faultings Theorem of curves, this would be the Galois action on the tape module. And we can try to show finiteness statements, or at least non-density, by showing two contrasting properties of this Galois representation. The first property is that only finitely many Galois representations can appear as the Galois representation of the fiber over an S integer point, can appear for a hypersurface with good reduction. And the second property is that if we look at the Galois representation over a p-adic point X, then we want it to vary a lot in some measurable way as X goes from one p-adic point to the next. So this first property is basically a result of Faultings Theorem, and it's kind of the same in every application of the method. And then finding new ways to understand how and like why the Galois representation should vary was like the key insight of Lorentz and Degenteich and what we're kind of building on here. So the first thing that you need to look at to understand how much the Galois representation varies from one point to the next is the action of the fundamental group on the cohomology of the fiber. And this is this very classical picture from topology where you have a cycle of cohomology in one fiber, and you can flow it from one fiber to the next smoothly. And then you find a loop in the base, and you flow it along a loop in a base, and you get another cohomology class in the same fiber, and that gives you an automorphism of the cohomology of the fiber. So the fundamental group will act on the cohomology. And there's a general principle that this action controls how the Galois representation varies. And so we need this action to be big in some sense. And the way we'll make that precise is the notion of monodroming. So kind of just restating, when we have our smooth and proper family, let's say the cohomology of the fiber has dimension n, we get a representation rho of the fundamental group into GLN over the rational numbers or over any coefficient field you like. And by definition, the monodromy of rho, maybe I should say Yx, is the Zariski closure of the image of rho. So this is an algebraic group, and we want to think of it not as an abstract algebraic group, but as a group with a particular n-dimensional representation. So you can think of, and I would like to think of for the beginning of this talk, the Lorentz-Venkatesh method as a black box. And what it does is it inputs your variety X with a smooth proper map from Y to X, and it outputs the statement that the S integer points are not Zariski dense when you put in some assumptions. The first assumptions are some numerical conditions on the Hodge numbers of the cohomology of the fiber, which are going to be less important for what I'm talking about today. And the second is the assumption that rho has big monodromy. And when I say big monodromy in this talk and in our paper, what I just mean is that the monodromy group must contain one of the three classical groups, SLN, SPN, or SON. It must be at least that big. In fact, if you look at the method, you could prove fineness for some smaller groups than this. You would just have stronger numerical conditions. So there's a trade-off between the two. And it's possible that in generalizations of the method, you will rely on smaller groups than the full SLN, SPN, SON. But for today, it's just those three groups. So if you trust me that this black box exists, then you can see how to prove the main theorem of Lorentz and Venkatesh about fineness or non-density of hypersurfaces. You'll plug in X, the moduli space of smooth hypersurfaces and projective space over the integers, Y, the universal family over X, I is the n-1, the cohomology in degree n-1 is the most interesting. And then the big monodromy assumption comes from a theorem which says that the monodromy of the universal family is always exactly ON or SPN, depending on if the dimension of hypersurface is odd or even, except specifically for cubic surfaces in P3. So in almost every case, the monodromy is either ON or SPN and therefore is big. And then this complicated condition on Hodge numbers I don't want to talk about corresponds to the complicated condition on N and D earlier that I didn't want to talk about.
All right, so strictly speaking, it's on the primitive.
Yes, strictly speaking, it's the primitive cohomology. Of course, if N is odd, if N is even, that's not a problem. But if N is odd, you want to take the primitive cohomology. So there's a very natural strategy given this non-density result to try to prove the full finiteness, which is some kind of Unitarian induction. So we show the integer points lie in some low dimensional subset of X. We would like to then apply the theorem again, replacing X with that low dimensional subset. And hopefully we can show they lie in an even lower dimensional subset. And if we can iterate this, maybe we can get the dimension all the way down to 0. At first, this idea seems to work pretty well. So if you have a map to X from Y to X, you can restrict that map to any subset of X, and it'll still be just as smooth and proper as it was before. If you had any conditions on the Hodge numbers of the fibers before, they're still going to be satisfied after you restrict. So the real thing that prevents us from doing an induction and getting the full finiteness is we don't know if our big monodromy is preserved. We don't know if we restrict to an arbitrary proper closed subset of X, whether the monodromy group of this representation will still be the same or whether it will shrink. And if you could, in any case, prove that the monodromy is always going to be big as you restrict to subsets, you could probably prove a similar finiteness theorem. But that's not exactly what we're going to do in Abelian varieties. We're going to do something slightly different. So now I'm going to explain the advantage of working with hypersurfaces in Abelian varieties that lets us get around this problem that we don't know how to restrict monodromy to subsets. So it's helpful to think here about an arbitrary family of hypersurfaces inside a fixed Abelian variety A, which could be the universal family of hypersurfaces, or it could be some very small subfamily of the universal family. So the nice thing about this family is that we don't just have one natural representation of the final group of X. We have many natural representations of the final group of X. And so because these are so important, I'm going to explain the construction of them in two different ways. So the first way will be more abstract, and the second will be more concrete. So if we have a character chi of the final group of A, we can take the twisted cohomology groups of the fiber with coefficients in the local system chi, or twisted by chi. And the fundamental group of X will act on this for the same reason it acts on the usual cohomology. You can flow these like twisted cocycles around from one fiber to the next. And we'll let this representation be rho chi. Alternatively, we can take a natural number m. There's a map from the abelian variety to itself, which multiplies every element by m in the group law, the multiplication by m map. Then we can take the inverse image of the fiber yx under this multiplication by m map. It'll still be a hypersurface in A, it'll still be smooth, but it'll be more complicated. It'll have a more complicated geometry. And let's look at the cohomology of this inverse image. The fundamental group will act on this cohomology by pulling cycles around from one fiber to the next. And the M torsion points will also act on this cohomology because they act as automorphisms of the fiber. And these two actions will commute. Because they commute, we can take an eigenspace of the M torsion points, whose eigenvalue is some character chi, and look at the action of pi1 on that eigenspace. And we'll call that representation rho chi. And these two correspond because we can express the fundamental group in terms of torsion points using the Tate module. So the really big advantage for us of having multiple characters chi is that to do the induction step, we only need to show that there exists some chi, such that the representation rho chi has big monodroming. We don't need to take a particular chi and show it as big monodroming. We just need to show there's at least one. And that additional freedom is helpful. That's sufficient for the induction, and that's exactly what we're going to do for an arbitrary non-constant family with some mild assumptions. So this is another great time for questions, and then I'm going to get into a little bit more of the details. So what I'd like to say next is what the precise statement of the big monodromy theorem we proved. So we're going to fix an abelian variety of dimension n. We're going to fix y to x a smooth family of hypersurfaces in A. We'll let phi be the class of a fiber, and we'll assume it's ample. And the conclusion will be that there's some character chi where rho chi has monodromy containing one of the three classical groups, SON, SLN, or SB. In fact, we'll show this for almost all chi. If you look at characters of the M torsion points, the proportion of chi forces that is true should go to 1 as M goes to infinity. And we're going to show this under three assumptions. So the first assumption is that Y is not stable under translation by any non-trivial element of A. And this assumption is certainly necessary, because if it was stable, that element would act on the twisted cohomology, would break it up into eigenspaces, and it couldn't possibly be big, because it wouldn't be an irreducible representation of the monodrome. The second assumption is that Y is not the constant family, and you're also not allowed to take the constant family and translate it according to some non-constant map from X to A and say now it's a non-constant family. Neither of those is allowed. And this is, again, certainly necessary, because in the constant family case, the monodromy would be trivial. And in the translation of the constant family case, the monodromy would be finite and contained in the scalar. So in either case, would we have big monodromy. And the third assumption is going to be our weird assumption on the n and the degree. And this is going to be the only one that isn't clearly necessary. It's a technical restriction. So if n is greater than 4, we have no assumption. If n equals 3, then the intersection number phi had better not be any of our binomial coefficients on that list from earlier. And if n equals 2, then phi squared shouldn't be a power of 2, although 1, 2, and 4 are okay. It shouldn't be 2k choose k, although 2 choose 1 and 4 choose 2 are okay. And it shouldn't be 56.
I have a question about the base of this induction. You keep on reducing the dimension, keep on using this large monodromy. When you get down to curves, do you use faultings or surfaces or?
No, we don't. So I'll show you. So we don't literally express it as an induction argument. We express it as a proof by contradiction. We assume that there's infinitely many, and we derive a contradiction. But you don't. I mean, you could, once you get down to dimension 1, use Faultings theorem, but we don't need to because we can just use our theorem again.
But your theorem seems to require.
So the only thing it requires is this non-constancy. That's like the only.
I thought you had some dimensions conditions, yeah.
Not on the dimension of x. So the dimension of a. But
okay,
a is fixed in our induction. So the only condition that, like, as a condition of the dimension of x that fails when x is a point here is the middle condition that's not a constant family.
Okay, thanks.
So this is a very weak condition, because of course constancy we wouldn't have big monodromy, and as soon as it's a little bit non-constant, we just immediately get enormously big monodromy. So I want to sketch quickly why this statement is sufficient. How can you conclude from this? I'm going to go over it quickly because I don't think getting all the details of this argument is important, but I think it's good to say. So we're going to kind of do a proof by contradiction where we assume that there are infinitely many different hypersurfaces and derive a contradiction from that. So we want to let x be the Zariski closure inside the modular space of smooth hypersurfaces of the set of all hypersurfaces with good reduction outside S. Or if there's multiple irreducible components, we'll pick one that contains infinitely many and have that one be X. And we can take Y to be the universal family of hypersurfaces on X, except that Y might be invariant under translation for something. So we first have to mod it out. So it's by anything it's invariant under translation. And so once we do that, once we mod out by any points Y is invariant under translation by, then Y will not be preserved up to translation by any non-trivial point of A. So we can verify the first assumption. Because we assumed that there are infinitely many different hypersurfaces that are not equal up to translation with good reduction, so that lying in X, we can conclude that X can't be constant up to translation. And so that verified the second assumption. And in dimension 3, because the original phi n was not a multiple of any of these weird binomial coefficients, then phi n of this quotient can be equal to any of these weird binomial coefficients. So because our family satisfies all three assumptions, we can apply the monodromy theorem and show some rho chi has big monodromy. And then by applying the Lorentz-Van black box, we conclude the integral points are not Zariski dense. And so this contradicts our assumption that there were infinitely many different hypersurfaces with good reduction up to translation. So I want to talk next about how this big monodromy statement is actually proven. And so the next part of the talk will kind of be more of an algebraic geometry. We won't work entirely number theoretically. And at the end, if there's time, I'll talk about the Lorentz-Van method and how we use big monodromy to get a non-density statement. So the key tool that we use to prove this big monodromy theorem is called the Tsunakian monodromy group. And in this context, they were defined by Kramer and Weishauer. And there's one for every smooth variety inside A. And if you know what a perverse sheaf is, I can tell you that there's actually a Tsunakian group for every perverse sheaf on A. This is a generalization because every variety gives you a perverse sheaf because you can take the constant sheaf and shift it and it'll be perverse. So that's a little bit abstract. Let me try to make it more concrete. So one part of their theorem is that if you take for almost all characters chi, you'll get the twisted cohomology of any variety Z, twisted by chi. This will vanish in every degree except for the middle degree dim Z. So it's a very common phenomenon in geometry. The most interesting cohomology groups are in the middle degree, And here that's extremely true, where the cohomology groups outside the middle degree just vanish. And so because these cohomology groups just vanish, you can compute the cohomology in the middle degree, compute the dimension by an Euler characteristic. It's equal to the Euler characteristic of the z times -1 to the dim z. And we'll call that number n. So the dimension of the cohomology group in degree dim z is always n. So what they really did is they defined an algebraic group, GZ, the Tsunakian monodromy group, inside GLN that acts naturally on the cohomology group for all like sufficiently nice characters chi, for almost all characters chi. So that's what the Tsunakian monodromy group is. So I'm going to give a definition of the Tsunakian monodromy group to explain what it actually comes from. But I don't think the definition is very helpful to understanding. So I'm going to try to give some intuition first. How should we think about the Tsunakian monodromy group?
Sorry, so are you saying that the that this monodromy group does not depend on the character chi?
Correct. It's similar to how the monodromy group of a local system on a variety does not depend on a point of that variety, but acts on the cohomology, or acts on the fiber at any point.
I see. Thanks.
It does. It depends only up to this. It's like if you care about it exactly and not just the isomorphism class, then it does depend, but we only care about the isomorphism class. So we can think of GZ as behaving very much like a monodromy group, but instead of living over some variety, we can think of it as living over the space of possible characters, even though that's not really a well-formed space. So the reason that's true is there's an analogy with a number of properties of the usual monodromy group. And the kind of slogan is that the usual monodromy group controls variation in the cohomology as we vary the point. So the monodromy of rho chi will control the variation in the cohomology twisted by chi as we vary the point x and fix chi. So what I mean by this is, well, if you look at look at any kind of structure of the cohomology, like look at the Galois representation of the cohomology, the Galois representation will normalize the monodromy group. And if we mod out the Galois actions at 2 different points by the monodromy group, which we can do because it normalizes, then the quotient actions will be the same. So if the monodromy group is very small, the Galois representations at different points have to be almost the same Galois representation. But if the monodromy is very large, Galois representations at 2 different points could be totally unrelated Galois representations. And if you look in the world of Hodge structures, the same thing is pretty much true if you think about Hodge structures using the Mumford-Tate group. And finally, there's the Sato-Tate property. If you think about varieties over finite fields, and you look at the characteristic polynomial Frobenius acting on the cohomology, then Deligne's equidistribution theorem tells you that the distribution of the characteristic polynomial Frobenius, if you look at a random point on your variety over a finite field, is controlled by the monodromy. It looks like a random element in a maximal compact subgroup of the monodromy group. So when I say that the Tsunakian monodromy group controls the variation of this cohomology as we vary the character chi and now fix the point x, what I mean is literally the exact same theorems hold. So it will be normalized by Galois groups in the same way, and there'll be this Galois constancy modulo the monodromy. And in particular, Sato-Tate theorems will hold. They will determine the equidistribution as you vary the character. And so this property of Tsunakian monodromy groups was studied heavily by Nick, for example, in his book on convolution equidistribution, and also in a paper or two. And Kramer and Weishauer ended up studying somehow very similar Tsunakian groups for very different reasons. They cared about not this kind of finite field equidistribution, but various kinds of complex geometry questions. And so we're using them kind of for a third reason to prove these big monodromy theorems that we need to solve our number theory problem.
Is there a translation that if you kind of big at some prime, then you, or most primes, then you big? Can you use such things?
Well, there's no reason to go to finite fields for our argument because
So why have you introduced it then?
Oh, I'm just
why have you introduced the Sato-Tate part of it?
I'm just explaining to provide some intuition.
You're not going to use it.
I'm not going to use Sato-Tate, but I'm saying, you know, some people here like Sato-Tate, and I wanted to explain this connection to Sato-Tate.
Okay, and you're not you're not going to be finding vanishing cycles and generators of the group either. I guess I'll wait and see how you make it big.
In a sense, vanishing cycles are used, but very indirectly. And we're not really finding generators. Well, sort of, yeah. I'll explain in a second.
Okay.
And is there some setting where this first sentence, this is a very interesting first sentence, you can give a rigorous meaning that GZ is a monodromy group of the space of characters?
No, I mean, so if we're working over the complex numbers, then we could say the space of characters is like a very well-defined space. It's like an algebraic torus. But I don't know how to make this monodromy group or this Tsunaki group literally a monodromy group over that space of characters. And it's very weird to me that you don't see in the group appearing in that setting. This is maybe even a bigger question in some kinds of geometric Langlandsy questions where you think about higher spaces of higher ranked automorphic forms. But yeah, I don't know any way to make this more rigorous than just by saying the same theorems all hold.
So before you introduce sort of two flavors of characters, Kai, are you talking about both of them right now? A and one came from like torsion.
Yeah, it doesn't matter which one we're working with. So you're supposed to work with whichever one you like more because they're the same. I mean, there's a natural bijection between the two different pictures. So you probably wouldn't let me leave if I didn't tell you what the actual definition of the Tsunaki group is. So let me now say what it is. The starting point for their definition is from constructing a very nice category of perverse sheaves on the abelian variety. And they define an operation on this category called sheaf convolution, which uses three different maps from the abelian variety, cross the abelian variety to the abelian variety. You can project into the first factor, you can project into the second factor, you can multiply. And so the convolution is defined by, you take two sheaves to convolve, you'll pull one back into the first projection, you pull that one back into the second projection, you tensor, and you push forward under multiplication. And this is formally identical to the usual like arithmetic or analytic notion of convolution on an actual group. And it behaves in this setting very much like tensor product. We can formalize that by saying it makes the category of perverse sheaves into a symmetric monoidal abelian category. And so Tsunakian category is any symmetric monoidal abelian category satisfying conditional axioms. And the beautiful main theorem of Tsunakian categories is any category satisfying these axioms is the category representations of some group. It's always a pro-algebraic group, an inverse limit of algebraic groups, and it's uniquely determined by the category. So the sort of big idea of Tsunakian category theory is a lot of times when you're constructing a group, it's best not to try to construct it by generators and relations or equations, but to construct it by first constructing its category representations as a category. And so we could define GZ as the Tsunakian group associated to the subcategory generated by the constant sheaf on Z, or another way of saying that is that we take the representation of this big group, this infinite pro-algebraic group associated to this constant sheaf on Z, and we look at its image inside GL. So this is the definition of the Tsunakian group. But don't worry too much about that definition because it may be better to think of it in terms of the big picture. So our strategy for proving the big monodromy theorem has two steps. We'll first fix a single smooth hypersurface in A, and we'll show its Tsunakian monodromy group contains one of our three classical groups. And we'll next consider a family of varieties in A, and assume the Tsunakian monodromy group of the generic fiber contains one of our three classical groups. And we'll conclude that for almost all chi, the usual monodromy group contains one of the three classical groups. So putting these two statements together, we get our main monodromy theorem. And so naturally, this needs all the assumptions that our main monodromy theorem has. So the first statement needs our assumption that H is not invariant in the translation, and it needs our assumption that we're avoiding this weird list of forbidden values. And our second statement needs the assumption that it's not a constant family. And even in this setting, the list of forbidden values may be a technical restriction. I don't know whether the weird, interesting monodromy groups actually show up, interesting Tsunaki actually show up for these objects. And the real advantage of Tsunakian monodromy groups for us is that they let us split the problem into these two parts. Because it turns out that an arbitrary family of hypersurfaces is a very nasty geometric object. There's not a lot you can do with it. It could have really very bad singularities. It could have very few singularities at all. We don't really know. But a single hypersurface, a single smooth hypersurface, is a really nice geometric object. We know exactly what it looks like topologically. We can calculate its Hodge numbers and other invariants. It's something really great. And so the advantage of this approach is we can do our hard geometric calculations in the Tsunakian world, where we only have to look at a single hypersurface H, not a family. So things are nicer. And then once we have the big monodromy group, we can transfer that information from the Tsunakian world to the usual world by an argument that's more abstract and that doesn't require precise information about the geometry. And so in the remaining time, I'm going to briefly explain each of these steps. So I'll explain the second step, which is more abstract first. This starts from this idea in topology that the fundamental group of the fiber of any fibration is always a normal subgroup of the fundamental group of the total space. And when we apply that in algebraic geometry setting, we'd rarely have fibrations in algebraic geometry. We like to look at families that have lots of singular fibers. So the algebraic geometry statement is the fundamental group of the generic fiber of a morphism is a normal subgroup of the fundamental group of the total space. And if we take that statement and we plug into a representation, we get the monodromy group of a representation, once you restrict it to the generic fiber of the morphism, is always a normal subgroup of the full monodromy. And so the basic strategy we're going to prove to transfer monodromy information from one Tsunakian group, from the Tsunakian group to the ordinary group, is we're going to make a big Tsunakian group which live over the space of pairs of a point and a character. And in this group, we should be able to prove that the usual monodromy group and the Tsunakian monodromy group are both normal subgroups, because the usual monodromy group is like the monodromy of a generic fiber, like generic chi will be a generic fiber of one projection, and the Tsunakian monodromy group of the generic point will be like the monodromy of the generic fiber of the other projection. So they should both be normal subgroups. And so because the Tsunakian group contains SLN, SON, SPN, the big Tsunakian group will contain SLN, SON, SPN. So it'll probably be a group like GLN, GON, or GSPN. And if you think about the normal subgroups of these groups, they're either big themselves, they either contain SLN, SON, SPN, or they're very, very small. They're contained in the scales. So by having this kind of abstract normalcy property, we only need to eliminate some enormously small groups, which are groups contained in the scales. So the argument is not purely formal or purely abstract. Proving these are normal requires some, direct geometric arguments, and eliminating the case where it's contained in the scalars also requires an argument, but it is more formal than just trying to calculate the monodromy directly. And so for the second part of computing this Tsunakian monodrome, we're going to take advantage of the fact that Kramer didn't just write this paper defining the monodromy group and give up, but he wrote additional papers proving a bunch of properties that are helpful for calculating the Tsunakian group. And the particular ones that will be helpful to us use an invariant called the characteristic cycle, which for hypersurface is just the cotangent line to the hypersurface at each point. And so, or at least for smooth hypersurface. So these results are pretty strong for smooth varieties and hypersurfaces. So they're very useful for a smooth hypersurface, although we have to do a little bit more work beyond what's in Kramer. So the theorem you get when you apply Kramer's results to a smooth hypersurface is that as long as
are we in an abelian variety necessarily, or is this more general?
Yeah, this is only in abelian varieties. Yeah, so yes. So Kramer's work is mostly about chief convolution in abelian varieties. For any smooth hypersurface in abelian variety, as long as it's not translation invariant by any non-trivial element, then GH must contain as a normal subgroup some simple algebraic group acting by an irreducible minuscule representation. So it's not very impressive to say that some algebraic group contains a simple algebraic group. Most of them do, but it's more interesting to say that it's acting by an irreducible minuscule representation. That's a much more rare condition. So what is a minuscule representation? That's a representation where the characters of the maximal torus that appear form a single orbit under the Weyl group. And these are completely classified. There's one for every algebraic group and every character of the center, or every of that algebraic group. And the example that you should think of is the wedge power representations of the special linear group are the only minuscule representations of the special linear group. So this statement about the characteristic cycle, it uses, the characteristic cycle is invariant that's important in the vanishing cycles theory of sheaves. And so this uses vanishing cycles of sheaves to try to understand their Tsunakian monodrome groups. And so this is done in Kramer's paper. And for us, this is kind of black box into a nice algebraic statement. So we are sort of using these kinds of local methods, and it's sort of giving explicit subgroups of the group, but it's also a more kind of abstract algebraic argument. So once we have this classification of minuscule representations, we have a very nice strategy to finish the argument. We just write down all pairs of a simple group with a minuscule representation. We cross off the classical group with a standard representation. Those are good, those are the ones we want. We just have to eliminate all the remaining pairs. And some pairs you can eliminate just for dimension reasons. So the dimension can't equal the dimension of the cohomology of our abelian variety twisted by Cobb. Can't equal our number. And that handles in particular all the exceptional groups and the spin representations, except in dimension 2. And so the really tricky cases are exactly these wedge power representations of SLM. And the way we eliminate those cases is we show they can only happen using some Hodge theory. We show it can only happen when a certain set of explicit equations are satisfied, and it becomes a purely elementary problem of combinatorics to find all solutions to that explicit set of equations, which is elementary, but it's really complicated. It takes us like 20-something pages of calculations and then a bunch of computer checks as well to handle that case. And then, but with those checks, we can find all the solutions, and that gives us the weird binomial coefficient from earlier. It's because our equation in dimension 3 reduces to Pell's equation, and those are the solutions to Pell's equation. And so, okay, it's probably a good place to stop because we're running out of time. I don't really have time to get to the last thing. Thank you for inviting me to speak.
Thank you for the lovely talk. Please unmute yourselves and let's clap for Will.
I have a question. The last time I saw you talking about these Tsunakian categories in connection with monodromy groups was your thesis. Was that useful to you here at all?
So certainly, if I hadn't thought about Tsunakian groups for a while during my thesis and at other times in grad school, I would not have come up with this strategy. I don't think I really used any specific techniques from my thesis, but the general knowledge of Tsunakian groups was very helpful here.
And you really need this for this problem?
I don't know any other approach. It's possible that somebody else will come up with an approach that does prove the same thing without Tsunakian groups, but I don't really have a clue what it could be. So it's precisely because I have to go really far back on this. Yeah, on this two-part strategy Like the Tsunaki groups very nicely allow you to split it up. And I think you'd have to do a lot more work, a lot more clever ideas to prove the big monodromy without splitting it in two like this.
Yeah, Peter, I thought a little bit about this. It seemed like an incredibly hard problem. I mean, I find it kind of amazing you guys could prove it in this case.
Amazing.
Do you think there's some notion of, so to speak, the right kind of hypersurface in a different kind of group scheme, like a big torus, that you could with?
Possibly. My guess would be that notions of a hypersurface in a torus with good reduction, you would, maybe there would be, maybe not. I'm just thinking about whether there would be a more direct argument. Like maybe it would end up being, maybe probably not. Because you could ask for, so you could ask for a family of hypersurfaces in the torus such that when you like embed it into like P1 to the end, you like compactify, then there's no vanishing cycles as you go from one like of the constant shape on the universal family hypersurface, or I guess of maybe no vanishing cycles of like a character shape. So this would imply, in particular, the rank of the cohomology would be the same. And in that setting, you would get character, you would get these character twisted cohomology, and you could try to use those in the same way. But we didn't think about how you could formulate that precisely, but it perhaps would be possible.
I'm just wondering if it's maybe somehow a sort of more natural question. Maybe it's not.
Yeah, I mean, I don't know. From a certain perspective, sort of every Diophantine problem is natural if it's like you can sort of solve it using some interesting geometry, but maybe that's a little bit too extreme. Yeah, I think the technical details of doing it in an algebraic torus would make it at least a little bit less natural.
But there is, you have landed up on subvarieties of abelian varieties or semi-abelian varieties where there are other Diophantine theorems of the second type, the Voiter type, which are very powerful. There's no, and you don't connect with that. There's no kind of Partian maneuver or anything where you might relate to Faultings second.
Yeah, I can't think of it, because if you think about our theorem, so we're working, if you want to think about our theorem concretely about integral points on some variety. Yeah. What is that variety? It's the modulated space of hypersurfaces with a given class. Right. Which is actually a projective space. It's a linear system. So what we're really counting integer points on is some open subset of projective space. And so it doesn't map into any abelian variety. So I don't think we could possibly apply Faultings' second theorem. So in some cases, when like the degree is very small, our like integer subset we would get like an affine, an open subset of like P1 or something. So you could apply like Ziegel's theorem.
Yeah, then you'd apply Ziegel, yeah.
Or like sometimes in P2, I don't know. In some cases, maybe you could apply Ziegel. But
you might be able to apply Zonier type things, yeah.
Yeah, so
they have some surface cases, but no, it's just I'm trying to relate it to the other method, which is really a Diophantine approximation theorem rather than a Shafarevich type theorem. As you know, his second proof is along the lines of Ziegel-Roth.
Yeah, I don't.
And it's funny that you're both landing up in subvarieties of abelian varieties as the setup.
Yeah, right. It's like, but if you think about it, I had a problem once. I was explaining this result to people verbally, and when you're explaining it verbally, it's very easy to get confused and think it's like the same result.
Yeah, right.
But it's actually very different.
Yeah. Thanks.
So I have a different question. It seems to me, so you're clearly using this convolution. So the abelian variety assumption is presumably essential. But what if instead of hypersurfaces, you wanted to do like complete intersections or something inside an abelian variety? Can you say anything about that?
So you absolutely could say something like complete intersections. The only thing is you would have to redo a bunch of calculations we did in a more complicated setting. So this, like this second part, works for any kind of subvariety of abelian variety. Could be hypersurface, complete intersection, not a complete intersection, whatever. But this first part, we use specific properties of hypersurfaces. And so checking that it's actually irreducible and minuscule would require some additional work. You'd have to go back to this work of Kramer, and then eliminating these minuscule representations would require some additional work. And like, because we wrote it, it was already like 20 something pages for us. We decided it probably wasn't worth trying to generalize to complete intersections, but somebody absolutely could, and it would probably work.
So you're saying the Kramer thing is the main obstruction to this?
So it's not just the Kramer thing. So there are these Hodge number inequalities that I didn't talk about. You'd have to check that. There are nice formulas for these Hodge numbers for hypersurface and abelian varieties. I think it's a little bit less nice for complete intersections, but it's still probably doable. And the second thing is, this work of Kramer. I think it's some of it specialized to hypersurfaces. You have to think a little bit for non-hypersurfaces. He was very interested in the theta divisors, which are hypersurfaces as always, and applying it to them. So that's why he wrote things for hypersurfaces. And then this last step of eliminating the minuscule representations, we don't use Kramer's step work to do that. We use concrete calculations, and you have to do different concrete calculations to handle the complete intersection case.
Thanks.
I want to stick on my question still. Maybe Kramer thought about this. Are these, I think, subvarieties of abelian varieties of this type are known to be hyperbolic by Green or somebody?
That sounds right. Yeah.
So is there any sort of geometry of that type that might be? Was he after something like that or not? I mean, you're saying that he was looking at the theta divisor.
Yeah. So I think his interest was mostly in the relationship to classification of abelian varieties. To, like, for example, a question is, can we recognize Jacobians by looking at these Tsunakian groups?
Yeah, right. Okay.
Can we use Tsunakian methods to show that we can recognize abelian varieties of certain types by looking at like simpler invariants of the theta divisor, like just the OI characteristic instead of the whole Tsunakian group? So that's the kind of question that he was looking at. He wasn't looking at these pure, like these mainly complex analytic questions to do with like hyperbolicity. So there is a hyperbolicity connection. To us, I think you can use our approach sort of indirectly to show that the moduli of smooth hypersurfaces in an abelian variety is hyperbolic in some of the relevant senses. So people have made conjectures about which varieties have fineness of integral points, and you can see that our result is compatible with these conjectures.
Oh, okay, good. That's nice. Yeah, so you're basically producing the variety and saying, ha, I can show you fineness.
Yeah. I tried once to like actually find explicit equations for varieties of this type, like to actually calculate the discriminant hypersurface of families of hypersurfaces in some kind of fixed abelian variety. And I didn't figure out how to do it to get reasonable equations in any interesting case. But it's probably possible if you put enough computational effort into it, you could find some case where you could actually get an explicit Diophantine equation, which you can show by this method has finally many solutions.
About effectivity.
Well, Brian was like refusing to answer questions about effectivity about his method, even in the case of curves, and it's clearly significantly harder to make it effective in our case than in the case of curves. So it's making it effective, in particular making it effective in any kind of reasonable time way is a slim hope, I think, and one should look first at Brian's method or the Lorentz Mechanisch method in the case of curves and trying to make that effective.
Regarding your previous answer about these discriminant loci, I mean, forget about the Abelian varieties. Can you make this explicit for hypersurfaces even? I mean, in projective space? For
some low degree and low dimension hypersurfaces, probably. I mean, I know, I think I can find people who have written down the discriminant polynomial for like cubic curves and like quartic surfaces in some of these examples. Certainly not. I mean, the Lorentz of Ekatish method, you start like their result, you need n greater than like 80 or something. I don't think anyone has written down the discriminant polynomials in dimension 80. But
Suppose you took as your abelian variety. So we work over, we can't do it over Q, an abelian variety with every good reduction. Even a self-product of elliptic curves with a CM elliptic curve with every good reduction, E cross E cross E a bunch of times.
Yeah.
So every good reduction. So are there hypersurfaces in it with every good reduction, in fact, or is that empty?
I don't know. So the our methods are certainly not strong enough to answer this kind of question. And you could look towards the methods which are sometimes able to use this emptiness, prove this kind of emptiness statement in simpler problems, like for abelian varieties and for some low dimensional types of varieties. And unless you're looking at very low dimensional hypersurfaces, then I think you're in trouble. So maybe, I mean, like, so the best case is if you're looking at a hypersurface inside a three-dimensional abelian variety, because it's only a surface. And for surfaces over the rationals, we know that they can't have good reduction everywhere if their H2OX is non-trivial. And I think for these surfaces in the abelian variety, the H2OX is always non-trivial, but we're over a field other than Q. So I think almost certainly not. Almost certainly there's no hope of proving this over any field that has abelian varieties with good reduction everywhere. I don't think. But it might be true. It could be true, but I don't know how to prove it.
If there are no further questions, let's thank Will again.